how can we define the Jacobi symbol? Let capital P be positive odd integer. It's not a prime, you remember, yeah, not that you should note that it is not a prime number. So we take a positive odd integer, that is capital P, and then we know that it has prime factorization. Capital P has prime factorization. That factorization is given here. Capital P equals P1 raised to A1, P1 to the power A1 into P2 to the power A2, etc. to PR to the power AR. Then P1, P2, etc. to PR are all prime numbers. They are all distinct prime numbers. A1, A2, etc. to AR are the powers of the prime number respectively in the expansion of prime power representation of the given odd number, composite number. Then the Jacobi symbol for this number is defined. Jacobi symbol for capital P can be defined. Sorry, yeah, see, the Jacobi number symbol, Jacobi symbol is a number. Jacobi symbol for a given another number, then there will be given a number n. A natural number will be given. Then the Jacobi symbol of that natural number with respect to the given odd number can be defined as given here. N bar P equal to the Jacobi symbol n bar P, where n is a given any natural number, be a given natural number. N bar P equals n bar P1 raised to the power of A1 into n bar P2 raised to A2, etc. The last one is n bar PR. See, the corresponding to this prime number, prime factor in P, prime factor of P, we have that number n bar PR, the whole raised to AR, and it's that quantity must be raised to the power AR, n bar PR, the whole raised to AR. So that can be, and this expression can be it can be represented using the product, the multiplication symbol, pi from, so that can be written as pi from I equal to pi, where I varies from 1 to r of n bar pi, the whole raised to ai. So pi of I varying from 1 to r of n bar pi, the whole raised to ai. Then you should note that very important points about this, about the Jacobi symbol are given here. Some important points are given. N bar 1 equal to 1 for all values of n, irrespective of the value of n bar 1 equal to 1. Should make by heart these things. N bar 1 equal to 1 for all n, and possible values of n bar p for any value of for any given odd prime number p. The possible values of n bar p are plus 1 or minus 1 or 0, plus 1, minus 1 or 0. So when do we get 0 as the Jacobi symbol? When n bar p, when if n bar p equal to n bar p equal to 0, if and only if n comma the GCD of n and p is greater than 1. See that 1 is there, it is greater than 1 is missing here. You cannot see that because that is outside that, when it is can't, then it is outside that range. Okay, if and only if you can see that n bar capital P equal to 0, if and only if the GCD of n and p greater than 1. Next, we have some explanations on this. We have you can see that the quadratic residue and quadratic non-residue using Jacobi symbols can be using Jacobi symbols. Yeah, it can be determined. Quadratic residues and quadratic non-residues using Jacobi symbols can be determined, just as in the case of Legendre symbol. See, suppose that suppose x square is congruent to, let's consider this quadratic residue equation. X square is congruent to n mod p. Consider where p is the capital number. Suppose x square is congruent to n mod p. Suppose that we consider this equation. After considering this, we suppose that it has a solution. Suppose x square is congruent to n mod p has a solution, and also let p is equal to p1 raised to a1, p2 raised to a2 into etc. to pr raised to ar. Then x square is congruent to n mod pi has a solution for all I. Where for all I, that means for when I equal to 1, 2, 3 etc. to r, for all values of I where I varies from 1 to r, it has a solution, and then this equation has a solution, because you can assuming that this expression has a solution, this equation has a solution, we can, what does it mean? It means that x square minus 1 can be divided by p, capital P. So when x square minus n is divisible by p, you know that since p contains p1, p2, p3 etc. to pr, all these prime numbers as factor, it contains p, capital P contains these prime numbers p1, p2 etc. to pr. So naturally you can divide the quantity x square minus n by any one of these prime numbers. You can multiply it by these prime numbers. Therefore you know, we get that n bar. Therefore, in that case, we get that solution. In that case, also for each value of pi, for each value of pi, the equation x square is congruent to n mod of pi has a solution. Yeah, because it is divisible by that quantity, because x square minus n is still, it is divisible by pi for I equal to 1, 2, 3 etc. to r. Therefore, since it has a solution, therefore n bar pi equal to 1 for all I, or when I equal to 1, 2, 3 etc. to r, we have n bar pi equal to 1. Therefore therefore n bar p equal to 1. Therefore we know that n bar p is equal to, then using, therefore hence we get that n bar pi equal to 1 for all values of n, and hence coming back to this the definition, using the definition of n bar p. See, since all these values are equal to 1, and here inside the bracket we have in each, here in, when we refer this this definition or this formula, n bar p, when we think about computing n bar capital P, it's equal to n by n bar p1, and that is equal to, we have found that we have seen that it is equal to plus 1 now. So plus 1 raised to a1 into, in the other case also, in this case also it is plus 1, so plus 1 raised to a2 into etc. plus 1 raised to ar. Thus we get finally the product will be then equal to 1. Therefore n bar p equal to 1, and that's why we write it here. N bar p, therefore n bar p equal to plus 1 as the products, since it's a product of a sequence of ones, a collection of ones, and their powers of 1, so we get the final value equal to 1. Therefore n bar p equal to 1. This method will not work in the case of, but you can see that this method will not work in the case of a quadratic non-residue. So coming back to this, therefore in this case we can say that n is quadratic residue mod p. So when this is quadratic, therefore when n is quadratic residue mod p, if n is quadratic residue mod p, we get that n bar p equal to 1. But in the case of non-residues, but we know that in the case of non-residues this method will not work. It's because if n bar pi equal to minus 1, if n bar pi equal to minus 1 for an even number of factors here, suppose n bar pi equal to -1 for an even number of fact is pi, then multiplying this multiple occurrence of pi is also considered here. We consider multiple occurrence of pi separately, we consider, and then we get that n bar p equal to -1 raised to an even number, that's equal to +1. Thus in that case we get that n bar p, still we get that n bar p equal to +1. That means n is a quadratic residue mod p, but actually what is the situation? N is not a quadratic residue mod p. So this is misleading, and this is because of this raising that power of -1 to an even number. So that is the reason. So this kind of misleading information or misleading idea will be the steps which is misleading to some wrong ideas will occur in some cases. So therefore in this case, the conveys of that above statement we have mentioned there in our previous discussion may not be true in this case. Okay. Thus this leads to the wrong conclusion that n is a quadratic residue mod p, but even if n is not a quadratic residue mod p, then we get that n bar p equal to +1. So it's misleading. Now properties of let's now discuss. Next we are going to discuss some important properties of Jacobi symbols. So these properties are stated there in theorem 9.9. Let capital P and capital Q be two odd positive integers. We take two odd positive integers, capital P and capital Q, then show that m bar p into n bar p equal to m into n bar p for any two natural numbers m and n. M and n are two natural numbers. Let's for proving this, let's consider the prime factorization of p1 raised to a1 to p2 raised to a2 into etc. to ps raised to as. And then you can write that using the definition of the Jacobi symbol, m bar p equal to m bar p1 raised to a1 into m bar p2 raised to a2 into etc. to m bar ps raised to as. Here it has the power as, m bar ps raised to as. So let's take this as the statement A. And you can write n bar p, n by changing m to n, we can write that n bar p equal to n by p1 raised to a1 into n by p2 raised to a2 into etc. to n by ps raised to as. Okay, then next as the third statement, let's consider mn bar p equal to mn bar p1 raised to a1 into mn bar p2 raised to a2 into etc. to mn bar ps raised to as. Now we can apply an important fact about, or an important theorem here, which states that the Legendre, but these quantities are Legendre symbols here inside the bracket. You can see each terms or each number. So each number is the Legendre symbol of the number mn with respect to p1, and here the second one is the Legendre symbol of mn with respect to p2. And also we know that Legendre symbol is completely multiplicative. Therefore, irrespective of the nature of m and n, you can split this quantity and get that mn bar p1 equal to m bar p1 into n bar p1. So that you can write it as the product of two Legendre symbol values. And not only that, in every bracket you can do that. Therefore we get here can now we get yes, this is that stated thing here. Applying this splitting procedure in every bracket, you get that mn bar p equal to m bar p1 into n bar p1 raised to a1 into m bar p2 into n bar p2 raised to a2 in every bracket, etc. and m bar ps into n bar ps raised to as. After that, you can now it has become inside the bracket we have ordinary multiplication of two numbers. These are the two numbers and ordinary multiplication. Here also you have ordinary multiplication. Now you can collect all the first numbers from every bracket together with its exponential value, and together with its power, you can take that is n bar. So we're collecting that and together writing it in a bracket, we get that m bar p1 raised to a1 into m bar p2 raised to a2 into etc. to m bar ps raised to as into m bar p1 raised to n bar p1 raised to remaining are n with are the numbers corresponding to n bar p1 raised to a1 into n bar p2 raised to a2 into etc. to n bar ps raised to as. And now again going back to the previous steps, so we have stated in statement A and statement B that this quantity equal to m bar capital P, and the second bracket quantity in the second bracket equal to n bar capital P. So these quantities are substituted and finally get the result is required, that is m bar p into n bar p. Okay, next we have the second property. We can prove the second property, which states that m bar p into m bar q equal to m bar p into q, where p and q are two odd prime numbers. Here p and q are two odd prime numbers, and since we can take that capital P equal to p1 raised to a1 into p2 raised to a2 into etc. to ps raised to as. We assume that capital P, we take the prime product representation of the number p, and all as well as we take it for the number q. Then you can now write m bar p equal to m by p1, referring this representation of p. We can write pm by p1 raised to a1 into m by p2 raised to a2 into etc. to m by ps raised to as, and also m bar q equal to m bar q1. See, these are the prime numbers present in the expansion of q. So m bar q1 raised to b1 into, because b1 is the power in the second case, b1 b2 are the power is p3 etc. So m bar p1 raised to b1 into m bar p2 raised to b2 into etc. to m bar qt raised to bt. And now next week what we can do, p into q, you can consider the product p into q, together p and q are considered, they are multiplied, but that has the representation p. It has a representation p 1 raised to a1 into p2 raised to a2 into etc. to ps raised to as into q1 raised to b1 into q2 raised to b2 into etc. to qt raised to bt. Therefore m bar pq can be directly written equal to m bar p1 raised to a1 into m bar p2 raised to a2 into etc. to m bar ps raised to as into, as its continuation you can write the terms corresponding to the key values. So m bar q1 raised to b1 into etc. to m bar qs raised to bt. And then that can be then written as two products here, considering the first set of values, first set of products of numbers. You can replace that part by m bar p, and the other part can be replaced by m bar q, and therefore m bar p into m bar q is equal to m bar pq. Next, the third property, says that m bar p equal to n bar p whenever m is congruent to n mod p. M bar p equal to n bar p whenever m is congruent to n mod p. So let us take the product representation, prime product representation of p, p1 raised to a1 into p2 raised to a2 into etc. to ps raised to as. Since the legendre symbol m bar pi, considering the legendre, we are going to consider here the legendre symbol again. With respect to that, in the case of legendre symbol, we know that m bar pi equal to n bar pi whenever, if and only if m is congruent to n mod p. We know that we have earlier we have verified that whenever m is congruent to n mod p. See, this is true for all values of I, for I equal to 1, 2, 3 etc. Yes, then we can use the above fact to get that we can use the above fact to get that m bar pi raised to a1 is equal to, therefore m bar p1 therefore m bar, when we take a1 the same power on both sides, therefore we can, if from this using this fact, using this information, you can write that m bar pi raised to a1 equal to m bar pi raised to ai. If it is a pi, then you have to take that it is ai. M bar pi raised to ai equal to n bar pi raised to a whenever m is congruent to n mod p, whenever m is congruent to n mod p. Okay, therefore we then combining or using this, and this is true for all values of I, therefore you get immediately that m bar p equal to n bar p whenever m is congruent to n mod p. Now we are coming we have to discuss the fourth property that states that a square into n bar p, a square into n bar p equal to n bar p, a square into n bar p equal to n bar p whenever a, the GCD of a comma p equal to 1. So this is true only when n is only when n is the GCD of a and p equal to 1. Using the first property, here we can use the first property. Using the first property, we have in general a square n bar p equal to first property. You can you should recall the first property. Using the first property, we can say that a square into n bar p is equal to a into n bar p. We can write that because you can split a square and it can be splitted. Yes, that is equal, that can be written as a into n, a into n, and therefore here we can write then a into n bar p, and then you can split it and write that see that property, applying that property, we can write that a bar p into a bar p into, this is a bar p into a bar p into n bar p, a bar p into a bar p, a bar p into a bar p into n bar p. Then you also know that a bar p equal to either plus 1 or minus 1. A bar p equal to, considering any number n, any number a bar p equal to plus or minus 1. So whenever this is true whenever a bar p is greater than whenever this is true whenever a bar p equal to 1. See, if it is greater than 1, we know that it is equal to 0. Whenever a bar p is equal to 1, the GCD of a and p, we know that a bar p equal to plus or minus 1 whenever GCD of a and p and capital P is equal to 1. If it is greater than 1, and then we have this value equal to 0. Okay, therefore suppose that okay, then next as the next step, in the next step we suppose that the GCD of a and p, it is greater than 1 and that equal to d. We assume that the GCD of a and b is not equal to 1, some number, it is d, and then that equal to p1 raised to a1 to etc to ps raised to as. Suppose p1 raised to a1 to p2 raised to a2 to etc to ps raised to as. Since pi divides a, then we know that pi divides a. Since pi divides a, okay, then we know that pi divides a, and so we have a bar pi equal to 0 for a bar pi equal to 0. Then for I equal to 1 2 3 etc to s, it's because for all values of I, pi is a factor of the common divisor, the GCD. The GCD of both the number a and p. Therefore, if you consider only the number, even if you consider only the number a, d can divide a. Therefore, p1, p2, etc. to ps can divide a, and that means a bar pi equal to 0 for all values of I, for I equal to 1 2 3 etc. to s, and that means a bar p equal to 0. So we get that a bar p equal to 0 whenever the GCD of a comma p is greater than 1. Remember that. So if a bar p if a comma p, if the GCD of a and p is greater than 1, then we have, then what is the value then for a square, and since a bar p equal to 0, in that case, you know, coming back to this expression, this is equal to 0, so that this quantity equal to 0, therefore total value equal to 0. Right hand side then becomes 0. Right hand side becomes 0, therefore a square n bar p equal to 0. We get the answer, a square n bar p equal to 0. But you know, in that situation you can see that n bar p may not be equal to 0. So in that situation, but a square n bar p equal to 0, it's because of the fact that the GCD of a and capital P is greater than 1. It's some quantity, there exists some quantity which is greater than 1. It is due to that we get 0 here and also 0 on the right side. But you know, the same time n bar p may not be equal to 0. That may be some number. Yeah, most often it is the number +1 or -1. So in that case, you know, what happens, this expression, this is not correct then. In that situation, it's because we get 0 here, but there may be situation where n bar p is not equal to 0, that is +1 or -1. It may be some quantity +1 or -1. Hence that leads to the conclusion that 0 is equal to either +1 or -1. That's a wrong conclusion, will be a wrong conclusion. Therefore we have to use the condition that a comma p, the GCD of a and p is not greater than 1. That means in order to this for this statement to be true, in order to become this statement true, you know, what is required? The condition that GCD of a and p must be equal to 1. That is essential. So this condition is essential. The GCD of a and p must be equal to 1. If it is greater than 1, then this equation may not work, may not be true. So using that, we can therefore proceed with this condition, assuming that a comma p, GCD of a and p equal to 1. Then you know, what happens then? We have to conclude then in that situation. If the GCD of a and p equal to 1, then we know that a bar p, you see, in general you can think about a bar p, that number, this is the Legendre, the Jacobi symbol. This is the Jacobi symbol because p is any odd prime number. So this Jacobi symbol may be +1, either +1 or -1. That value, you know that this value will be +1 or -1. So when we come to this expression a square into n bar p, that equal to, in the expanded form, you know, that value equal to this is that value. Then a square n bar p equal to a bar p into a bar p into n bar p. But you know, this quantity is suppose this quantity is +1, then we have +1 into +1 product is +1. But if it is -1 to -1, then also we get +1. Hence we get that that you can see that this quantity, right hand side quantity, reduces to the expression n bar p. Okay, and therefore irrespective of the value of a bar p, whether it is +1 or -1, since we are taking the product of the same quantity, since we are considering the square of that quantity, so there we get 1, and hence that right hand side reduces to n bar p, and therefore we get a square into n, the whole bar p is equal to n bar p. Okay, that is the end of the properties of important properties of the Jacobi symbol. So okay, therefore thank you for listening. Okay, thank you.